So this is the steam main. In thermal power plants, you can observe this. In a steam pipeline, the steam is passing through the pipeline, and if you want to find out the quality of a steam, what is the quality of that particular steam? So there is one experimental setup is there. So with that experimental setup, where you can easily estimate the quality of a steam. So this is the theoretical points which are mentioned over here. So if the pressure is given, the saturation temperature gets automatically fixed for this substance. And this particular content I have covered into the saturation curve, where the saturation curve is nothing but the representation of the saturation pressure and the saturation temperature. So the in the measurement of a quality, the object is always to bring the state of a substance from the two-phase region to the single phase or superheated region, where both the pressure and temperature are independent and are measured to fix the state either by adiabatic throttling or electric heating. So in throttling calorimeter, a sample of wet steam of mass m at a pressure P1, which is taken from the steam main pipeline through a perforated sampling tube, So related to this one, the quality of steam, after finding this one, because in a throttling calorimeter, and already we have learned so much from the uh, throttle valve or the throttling calorimeter, where the enthalpy remains constant, but the entropy is greater than zero. That means here the entropy is going to increase slightly in a throttle valve. So this H1 is going to become as HF1 plus quality of steam into HFG, and this H2 which is in the superheated region. Then with this case, where you can find out the quality of a steam from this particular experimental setup. So the point P2 and T2 which is in the superheated region, So suppose if you draw the HS plane, if you draw the, that is enthalpy versus entropy, this you can also call it as a Mollier diagram, right? So this is the Mollier diagram, that is the x is equal to 1, quality of steam is 1, that means pure vapor is present, no liquid droplets. And if you draw the two constant pressure lines, these are the constant pressure lines. So this is the P2 and this is the P1. This is the P1, constant pressure line, right? So when you draw this particular case, then this is the point, that is enthalpy H1 is equal to H2. What is this enthalpy H1? This H1 is equal to HF1 plus X1 into HFG is equal to, this is in the superheated region, because this is nothing but the degree of a superheat. So this is point 2, that is the T2, which is in the superheated region. Then you have to record the H2 is nothing but superheated steam property, And with that one, where you could able to find out the quality of a steam. So the throttling calorimeter is used to find out the quality of a steam. Throttling calorimeter is used to find the quality of a steam, right? So this is all about the throttling calorimeter. Like that one, there is a separating calorimeter is there. And the combined separating and throttling calorimeter is there. Combined separating and throttling calorimeter is there. So when you draw the TS plane, that is temperature versus entropy, the representation of the, because the throttling process is nothing but it is a irreversible process. So that's why the irreversible process is represented in a dotted line. See here, this is the irreversible process. It is represented in a dotted line. So this is the quality of a steam. This is the, here say the quality of a steam is 0.9. So H is equal to, H1 is equal to HF1 plus X into, that is X1 is equal to 0.9 into HFG1 is equal to H2, which is in the superheated region, and you have to record that particular superheated region temperature. Okay. So that you have to observe this particular thing. And a small experimental setup which is showing over here in order to understand the meaning of a throttling calorimeter. To understand the meaning of a throttling calorimeter.
Today we will discuss about throttling calorimeter. Firstly, we will discuss about what is calorimeter. We know that calorimeter is an object for measuring the heat capacity of the chemical reaction. And in the throttling calorimeter, firstly we will discuss about all the parts of the throttling calorimeter. We have a outer chamber and a inner chamber with connecting pipe. This is a sampling tube for transfer steam to the inner chamber. This is the steam condensing chamber in which steam will be condensed. This is connected to the outer chamber, and these are the baffles or restriction for the steam. This is the thermometer. This is the oil in this chamber. This is the throttle valve or orifice from which steam will be throttled and passed to the inner chamber of the throttling calorimeter. This is the pressure gauge for measuring pressure of the steam before going to throttle valve. Now we see the working of throttling calorimeter. When steam will come through the sampling tube, when steam will come, then it will pass through this throttle valve and become superheated. And this superheated steam will go to the inner chamber of the throttling calorimeter. In the throttling calorimeter, it will go in the downward direction and then upward direction. It will reach to the outer chamber, and from the outer chamber it will go to the steam condensing chamber, and in the steam condensing chamber this will be condensed into water. Now this is the working of throttling calorimeter. We can calculate dryness fraction to throttling calorimeter by some readings. Note, before sampling, pressure of wet steam before throttling we have to calculate or we have to measure. Temperature of wet steam we have to measure, and for after sampling of the wet steam, steam will be superheated, so pressure of the superheated steam will be calculated and temperature of the superheated steam will be calculated. After this, steam table will use for the further calculation for measure the dryness fraction of the throttling calorimeter or for the steam. Thank you for seeing this video. For more updated videos, you can subscribe me on my channel.
You can also listen this particular video lecture.
Today we will discuss about throttling calorimeter. Firstly, today we will discuss about throttling calorimeter. Today we will discuss about throttling calorimeter.
Okay, so this is how the things are connected. Now here onto the enthalpy versus entropy plane. Enthalpy versus entropy plane. So the calculation of this particular thing, how these things are connected to this particular side. That is, this is the low quality. That is where you can find the quality here. This is the superheated state condition. At and from 100 to 105, minimum degree of superheat is required in a throttling calorimeter. So it has to reach, if it is 100 degrees centigrade, is the T1 is 100 degrees centigrade. In a throttle valve, it has to become to the minimum 5 degree centigrade degree of superheat. So that it is going to indicate the minimum quality that can be measured only by throttling is that is 5 degrees centigrade. So to be sure that steam after throttling, see here, after throttling steam, this is the dotted lines representation. Steam after throttling, it is in the single phase or superheated region. A minimum of 5 degrees centigrade superheat is desired. If the pressure after throttling is given and minimum 5 degrees centigrade, superheat is prescribed, and then there is the minimum quality of a steam. at a given pressure and temperature that can be measured by throttling calorimeter. So for a throttling calorimeter, minimum 5 degrees centigrade of a degree of superheat is required. Minimum 5 degrees centigrade superheat is required. Next, a separating calorimeter. What is the separating calorimeter? That how you can find out and what is the meaning of this particular separating calorimeter? So in that case, if you just observe that in this type of a calorimeter, the known mass of a wet mixture is collected through a sampling bulb, that is this one, through a sampling bulb and sent to a separating chamber. See, this is the separating chamber. The separating chamber has a series of obstacles and zigzag path inside it so that when mixture passes through them, the liquid particles get separated due to the sudden change in the direction. The liquid particles are separated over here and the gas is going to move out. Change the direction of flow and gravity. Liquid thus separated out is collected in the collection tank and is measured. Thus, by knowing the two mass values, dryness fraction can be estimated, and this dryness fraction is equal to total mass of the mixture minus mass of the liquid divided by total mass. So that you can observe. So listen this video lecture.
Today we are going to discuss about separating calorimeter. So welcome to my YouTube channel Mechanical Engineering Management. So it is used to measure dryness fraction of the steam, but it is very wet. So let's try to draw the figure of the separating calorimeter step by step so you can remember it, and definitely you can draw the same separating calorimeter in the examination also. So this is the outer chamber and this is the inner chamber. Having some special shape, and that is actually the separating cup, and that's why it is called as separating calorimeter. And this is connection of the steam pipe to the calorimeter, and that steam pipe that is actually connected with stop valve. So this is called as stop valve, or you can say control valve, and that is connected to the steam main pipe. And this pipe is known as sampling tube with perforation. Very small holes are provided on the circumference, and that is connected with the steam pipe. So you can say this is the main steam pipe. So from the main steam pipe, the steam comes to the separating calorimeter. And this end is also perforated. Inner chamber that is connected with water level indicator. So this is water level indicator. An outer chamber that is connected with pressure gauge. So this is pressure gauge. So the pressure is measured with the help of the pressure gauge. And that is valve that is attached to the outer chamber, that is called as the stop valve. Now what happened during the process? So here the steam that is came from the main steam pipe to the calorimeter to the control valve. This is called as the perforated cup. Sometimes it is called as the separating cup. So the steam is actually wet steam. So some of the water molecules are exist in the steam sample. So that water molecules collected over here due to the inertia, and that water molecules next collected in the inner chamber. So I can write over here water, and this water level that is actually measured with the help of the water level indicator. So you can see over here. So whatever it may be the level over here, that you can see from the water level indicator. And the amount of the steam in the sample steam that is reflected over here from the perforated cup due to the light density, and that will be through the annular space to the stop valve. So here you can say this green color is actually the steam. Due to the light density, it will come over here, and then it is discharged to the barrel calorimeter, where the weight is measured. So this is a very simple figure, and definitely you can draw in the examination. Now let's discuss with the important characteristics. First, the working. So the steam is supplied to the calorimeter from main steam pipe through a sampling tube. So this is the sampling tube where it strikes to perforated cup. So this is the perforated cup. Due to the inertia of droplets, water particles are separated and they are collected in the inner chamber. The steam is condensed in barrel calorimeter. So steam is condensed in the barrel calorimeter where the mass of the steam is measured. So whatever it may be the steam that is collected in the barrel calorimeter, so you can measure the mass of the steam that is in the main steam pipe. And the water particles are gathered in the inner chamber, and so that you can measure the mass of the water particles. So that is MS and MW. So mass of water droplets is measured with the help of the water level indicator. So the calculation for the dryness fraction of the steam. So as you know that formula of the dryness fraction of the steam X is equal to MS upon MS plus MW. So you know that MS and MW, so you can put it over here and so that you can find the dryness fraction of the steam with the help of the separating calorimeter. Limitation of the separating calorimeter. It is used for very wet steam only. It gives approximate value because of some of the water molecules can flow with the steam molecules. X is always greater than actual due to incomplete separation of the water over here. So these are certain limitations for the separating calorimeter. The application. It is used to measure dryness fraction of the very wet steam only. So thanks my dear friends. Press the like button to appreciate this video.
So this is what the steam separating calorimeter. So like that one, there is a combined separating and throttling calorimeter is also there. So this is the diagrammatic sketch. You please go through that one and try to find out the quality of a steam and identify its significances. When at what time you have to go for the throttle calorimeter, at when you have to move on to the separating calorimeter, and then what is the necessity of separating and throttling calorimeter. So all these things are covered onto that particular side. So here the degree of superheat and subcooling is mentioned. The degree of subcooling, this is the degree of a subcooling process, and this is the degree of a superheating process. So all these particular things are mentioned over here. Okay. So already we have covered what is meant by compressed liquid and what is meant by that particular thing. So in the next class, I am going to cover the Clausius-Clapeyron equation, that is video lecture number 34. So thank you for listening this particular class. Thank you one and all.